we will be dealing with some experiment which will involve spectrometer like angle of prism, refractive index, Cauchy constant, dispersive power, resolving power, and even some experiments of grating also. Okay, so there are 6-7 experiments which involve this usage of the spectrometer. So I will give you the basic idea how this spectrometer looks like, how we can use it, and how we can take observations from this spectrometer. We will be using, of course, we will be studying for all these experiments. We will be studying reflection, refraction mostly, and we will also be seeing diffraction in case of diffraction grating and all other experiments. So this spectrometer, see, this is the picture of spectrometer. There are various components in this spectrometer. The major components are the collimator, the prism table, and the telescope. This collimator is actually used to take light from the source, and these light rays will fall onto this prism which we are placing on the prism table. And whether reflection happens, whether refraction happens, we will study those patterns, we will study those light rays with the help of this telescope. Okay, so light will come from this collimator from this end, and light will pass through this collimator, it will fall upon the prism, and either after reflection or after refraction, it will pass through this prism, and we will study the observation, we will study this light ray, how it is bending, how it is after reflection or refraction, how it is bending with the help of this telescope. And both of these collimator and telescope, how they are aligned when you are viewing the particular light ray in this configuration, let's say, then what are the observations, what is the angle, what is the inclination of this telescope with respect to the collimator, on which angle this telescope is placed with respect to collimator, we can find out with the help of this scale. In this spectrometer there are circular scale for noting the reading, and these readings are actually basically these are the angle between this collimator and telescope, how this angle is changing. You have to move this telescope, to find the either the reflected ray or the refracted ray. And yes, in the center of this telescope you will be viewing from this end, this is called eyepiece. From this eyepiece you will be viewing the reflected or refracted ray from the prism. And on the center of this, if your slit, now I will use another word, this is your slit, a source light will be enter into this collimator through this slit only. This light ray, a parallel light ray will travel through this collimator, it will fall upon the prism, it will reflect or refract from this prism, and we will be viewing this light ray, this slit from this telescope. And if I place the crosswire of, again I am using another word which is crosswire. Crosswire is actually used to ascertain the position of the slit. Crosswire is in the middle of this eyepiece. You will see a line in the middle of this eyepiece. When you will be viewing from this, you will see a line in the middle of this eyepiece, and that crosswire, that line, that crosswire is used to you can say fix the incident light. You can to fix the position of the slit. you have to use that crosswire. I will be showing you in the experiment how you are using this telescope, how you are using this collimator, how you can use this slit to change the width of the uh, source light incoming into this collimator. Okay, there are some more things for reading. Of course, for taking observation, we have to use this circular scale beneath the prism table, and these are actually some more settings which allows us to either rotate the telescope freely in horizontal direction or to fix the telescope. This red circle is to fix the telescope, or if it is freed, then you can rotate the telescope also. Means this third lever, this lever is actually used to either constrain or allow the motion of this telescope. Similarly, there is another knob which is used to constrain or allow the motion of prism table, right? And there are some more screws to level this thing, whether it is vertically leveled or not. Of course, for horizontal leveling also there are some screws. Again, on prism table, on this table where all the reflection and refraction will happen, there are more screws which can be used to make this horizontally level, horizontally plane. Okay, so if I talk particularly about this collimator, now I am zooming the part of this spectrometer one by one. I will talk first about this collimator. See, this collimator on my right hand side, this has adjustable slit, and this slit can be used. See, by rotating this screw, you can either increase or decrease the width of the slit, which will allow the light passing through this collimator. तो इसको जितना खोलेंगे उतना वाइड स्लिट अंदर आएगा. वाइड आपकी स्लिट बनेगा. जितना कम करेंगे उतना आपका नैरो स्लिट बनेगा. So it has to be adjusted in such that there will be a sharp line of the light rays. This screw is used to change the position of convex lens. This is your convex lens, and why we are using this convex lens, I will show you. To change the length of this convex lens, we can use this particular screw. So in short, this collimator is made up of two things. One is adjustable slit, another is your convex lens, and the distance between this slit and convex lens can be altered, can be adjusted, can be changed with the help of this screw. Okay, so a collimator is consist of a tube having rectangular slit of adjustable width and length. Of course, I can also change the length of the slit as well as I can change the width of the slit at one end and convex lens at the other end of the tube. When length of tube is made, okay, now the physics part comes. When the length of this tube, this collimator tube, is made equal to the focal length of the lens with the help of this adjustable screw, then parallel beams are produced. As you know, suppose here is the source, here is the collimator. You are placing the source onto the just beneath the collimator, and here is the convex lens of the other right hand side part of the collimator. So the length of that collimator should be such that the focal point of the focus of this convex lens should be at the source. And if light source is placed at the focus of this convex lens, then after coming out from this convex lens, these rays, this diverging wavefront will be converted into a parallel beam of rays. So with the help of that adjustable screw, what we have to do is we have to change the length of collimator such that the focal length of this convex lens matches with the distance from this convex lens to the source. Now after seeing this figure, you will understand more clearly this thing. This screw will change the length. This screw will change the length between convex lens and the source. Source will be placed here. Source will be placed just before this adjustable slit. This adjustable slit will be used to create a good, bright, narrow slit of the source. And this screw we have to rotate so that this convex lens will produce a parallel beam of light rays coming from the source. And these parallel beam of light rays will be passed on to the prism table. They will be passed after creating a parallel wavefront. You can say they will be passed towards the prism. Now, okay. Now, after either being reflected or being refracted from the prism, we will watch how the angle of these light rays, are changing after either reflection or refraction. And these light rays will be viewed with the help of a telescope. Again, in telescope, so you can say, okay, again in telescope there will be one convex lens, another convex lens. This convex lens we call as eyepiece, and at this point your eye should be there. Your eye should be at this point. So again, if I think about this, a parallel beam is coming to this convex lens. This convex lens will converge these parallel beams into a point object, into a point object. So these will be converged at this point where your eye has to be stationed, right? Where your eye has to be stationed. So you can say telescope is used to observe the spectra generated after refraction or reflection or diffraction. Anything can happen at the prism table, that is different thing. But yes, collimator will produce a parallel beam ray. Something will change on the prism table, and you have to observe that change from the telescope. And this telescope is very simple astronomical telescope with eyepiece. And there are some types of telescope. Which type of telescope is it? It is Ramsden type of telescope, in which there are two convex lens. The focus of this convex lens is in between this telescope, and again the rays will slightly diverge and they will hit this convex lens of this eyepiece, and they will again be converged into this at this point where your eye has to be stationed, right? And this is again, there is a screw for adjusting the distance between this convex lens and the eyepiece. Okay, and in between this there are crosshairs. I will show you how these crosshairs will look like. और क्या लिखा है? The eyepiece is adjusted with the help of screw to observe a sharp image. So if a parallel beam is entering from this side, then it will be converging at any point. It will be slightly diverging again, but yes, because of this eyepiece, it will be converging at a point, and it will form a sharp image of the slit. It will form a sharp image of the slit. Now, the prism table, where all the physics will happen, either it will be reflection or refraction. So on this prism table, I can either place a prism, glass prism, or I can either place a diffraction grating. And due to these materials, either it is prism or it is diffraction, there will be some change in the incident slit. There will be some change in the incident light. This prism table is a circular table with adjustable height. Yes, you can change the height of this prism table so that it is collinear with the telescope and the collimator. It can be leveled horizontally with the help of these three screws. You can level this so that there will be no tilting of this prism. This should be exactly horizontal. Prism or diffraction grating will be placed on the table. Whichever experiment you are doing, depending on that, either we have to use a prism or we have to use a diffraction grating that has to be placed, that has to be attached to this prism table. Prism is placed in such a way that the refracting edge is perpendicular to the plane of prism table. Refracting edge is perpendicular to the plane of prism table. So if I talk about prism, see, it will have different faces. Out of these different faces, two faces will be transparent, two faces will be transparent, and one face will be rough, okay. Just like this, you can see the above surface is rough surface and these are polished surface. Polished surface means they are transparent surfaces, okay. So they are transparent surfaces, and light can enter through these edges, but light cannot enter through this edge because this is rough one. There will be more dispersion of light if you try to give light to this surface. There will be more dispersion and uh, dispersion to the surroundings, okay. Now the point is how we can calculate the observations which we will be observing, okay. How we can calculate the value of angle at which this collimator and telescope is aligned, at which this collimator and telescope is aligned. So for that, we have some circular scales on this prism table. We have to take observations of this circular scale. You must be familiar with these type of scales because you have done screw gauge experiment, right? So first of all, before taking any observation, we have to find out the least count. We have to find out the least count of this particular circular scale, right? So as scale is circular, so we will talk in degrees, minutes and seconds, okay. The minimum degree is 0 and maximum is 360. The whole circle will complete 360 degrees. Now you have to see in each and every spectrometer, this can slightly change, but for this figure I will say in between 90 and 80 degrees there are 20 divisions. There are 20 divisions between 90 degree and 80 degree. So one division corresponds to half degree. Half degree means 30 minutes. 1 degree is equal to 60 minutes. 1 minute is equal to 60 seconds. So one division corresponds to this main scale division. A single main scale division corresponds to 30 minutes. And you can see above, you have 30 divisions on your vernier scale. We have 30 divisions on your vernier scale. So if you look it carefully, then you will see 30 vernier scale divisions are coinciding with the 30th VSD will coincide with 29th MSD, 29 main scale divisions. So you can say one VSD, one vernier scale division is equal to 29 divided by 30 main scale division. And the least count of these type of scales are one main scale division minus one vernier scale division. So if you calculate this, if you solve this 1 main scale division minus 29 by 30 main scale division, it will come to be 1 by 30 main scale division. And you know main scale division is of 30 minutes. So 30 minutes divided by 30 will be equal to 1 minute. That's why on the top of this figure you will see there is written vernier 1 minute. So the least count of the angle which we can measure from this type of spectrometer is 1 minute, okay. But remember one thing, we just want to find the angle between the collimator and the telescope, and the minimum angle which we can find with the help of this vernier scale is 1 minute, okay. So again another example of the same thing is given. Suppose there is some scale which has divisions like this. So you can see the main scale division from 20° to 30° has 10 divisions, right? Has 10 divisions. So each main scale division corresponds to 1 degree. Each main scale division corresponds to 1 degree. And if you try to find out the least count of this, you will see there are 10 vernier scale divisions. Okay, you will see in this case there are 10 vernier scale divisions which are equal to 9 main scale divisions, and one main scale division was corresponding to 1 degree. So in this case, one vernier scale division with respect to main scale division is equal to 9 by 10 MSD. So least count is 1 main scale division minus 1 vernier scale division. So if I calculate this, it will be 1 minus 9 by 10, and I will take common main scale division. So it will be 1 by 10 of main scale division, which is 1 degree, or I can say 60 minutes. So it will be 6 minutes. So the main scale, the least count of this particular device will be 6 minutes. The least count of this particular device will be 6 minutes. So okay, now at this position I have to find the total reading of this at this particular point. Now you know, I will use the total reading of any of any scale of this type will be equal to main scale divisions plus I will say VSR. Okay, so main scale division plus vernier scale reading, main scale reading and vernier scale reading. So in this case you will see, okay, to take the observations, how you have to do it. The zeroth of this vernier scale, is actually, okay, is actually, you have to see just the main scale division just before the zero of this vernier scale, the main scale reading just before the zero of vernier scale division. So can you tell me what is the reading just before the zero of this vernier scale?
19.
19. So main scale reading will be 19 minutes. Will be 19 minutes. And you have to see which line is actually matching with the main scale division. So you can see 1, 2, 3, 4, 5, 6, 7, 8 is matching exactly with the main scale reading. So I will write the vernier reading is 8 and the least count was 6 minutes. So the vernier scale reading, you can say vernier scale reading is 8 into 6 minutes, that is 48 minutes, and the total reading will become 19 degree 48 minute in this case, right? So each and every spectrometer has different type of vernier scales. You can have, you will see, if even in offline mode we have spectrometers which have 30 divisions in vernier scale. We have some spectrometers which even have 60 divisions on vernier scale. Even the main scale readings can also change. It depends on the type of spectrometer which we are using, but yes, for all these type of spectrometer you have to first calculate the least count, otherwise you cannot find that main scale reading, otherwise you cannot find the total reading. Okay, so I will just show you how these things look like. For using this, you have to search a web page which is called, you just have to type optics lab on the Google. You can type optics lab VL Amrita, virtual lab Amrita. So you will, on the first you will see optics virtual lab physical science, right? On this page you can see there are lot of experiment which we will be performing. Okay, so just I will take some basic experiment. Angle of prism using spectrometer is a basic one. When you click on this, it will give you some basic theory about it, about this experiment. Okay, how we have to perform this. It will give you some procedure about it. Okay, some question and answer about this, and the animation about this. Okay, and the simulator. The simulator is actually link for the virtual lab. The simulator is actually link for the virtual lab. But you can, I think you have to log into this VL lab, this Amrita, uh, uh, V lab Amrita. You have to log in into it, but you can log in into it with the help of your Gmail credentials. With your Gmail ID and your password, you can create an account on this VLab, and it is very easy, very simple step. Okay, so okay, now see. Okay, before going into this, I just want to discuss some more things. See, before using any spectrometer, before using any spectrometer, there is very basic and very important uh, focusing, which is called Schuster's focusing, Schuster's method or Schuster's focusing, which has to be done, with the spectrometer. And this Schuster's focusing says if this is your collimator, this is your prism table, and this is your telescope, then and this is your source. This Schuster focusing says the prism should get only the prism should get only parallel beam of light falling onto it. This incoming beam cannot be divergent. This beam cannot be divergent. This has to be parallel beam. And you know, okay, and of course, if second case is this prism has to receive a parallel beam only, and again this telescope is fixed such that the length of this telescope and other setting of telescope is such that when parallel light rays are coming to this, when parallel light rays are coming to this telescope, then a point image should be formed at the end of the eyepiece. A point object should be formed at the end of the eyepiece. So all these settings are actually described by this Schuster's, and this Schuster says to check whether our collimator or even telescope is perfectly aligned in these conditions, that settings, that focusing are called Schuster focusing. And how we can truly establish that this telescope is aligned in this way, that whenever a parallel beam enters into this telescope, a sharp image will be formed at the eyepiece. This you have to ascertain. For this, what we can do is we can move this telescope into a complete different direction, and we can focus on a distant object. We can focus on a to calibrate, I can say, to Schuster focusing, I can say, what I have to do is I have to focus the telescope on a distant object, See, I do not know whether this collimator is creating a parallel beam or not. But yes, if I move around this telescope from this prism table, from this collimator, and if I just look outside the window of your lab, you can say outside the window of your lab, and you just want to see the image of a very distant object. Now, distant word I am using because a distant object always create a parallel beam of light on the receiver. A very distant object will always create a parallel beam of light on the receiver. Okay. For example, suppose if there is a light source, then as far as you go from this light source, if you are at this point, you will see this is a divergent wavefront. But at this point, you will see this the wavefront is slightly divergent now, not very much divergent. But at this point, if you see, you will feel it is a parallel beam. Okay, more is the distance between source and receiver, more will become the divergence of this wavefront will become less. So to find out to find out the exact length which we will be requiring to convert these parallel beams into a point object, we will place this telescope, we will direct this telescope on a distant object, right? And all these type of settings are called Schuster focusing, and this is your homework. You have to read about this Schuster focusing. There are some more steps to do this. So yes, this particular, when I will come back to this web page, this shows, okay, now what he is displaying, what they are displaying, they are saying the image, as you can see from this telescope, is something like this, and you have to change the length of this telescope by, you have to focus this telescope by changing the length of this eyepiece and this convex lens, which you can do by dragging this line. You can see if I click on this and if I drag, then the image will change, right? This image is changing as I am dragging this. Now at this point I can see my image is sharp, my image is sharp, right? So yes, I can say that for this particular length between this focusing, between this eyepiece and this convex lens, this particular length is absolutely the case in which the parallel beams from a distant object is forming a very sharp image on the eyepiece, on the eyepiece. So after focusing this telescope, even in offline mode, you were supposed to do this thing. After focusing this telescope, you have to do this thing. Next thing is, now you can see this is your source, light source, this is your light source, this is your collimator, this is your prism table, and this is your telescope. And instead of viewing this, whatever the view of this telescope, they are displaying on this circular black portion, right? So if I switch on the light, you will see there is a slit. This light is entering through this collimator end. You can change the slit width, you can change the slit focus. Slit width you can change by rotating this screw. Slit width can be changed by rotating this screw, and slit focus can be changed by rotating this screw. Okay, the distance between the convex lens and the slit you can change with, and the slit focus will be changed. I will show you. So basically what is happening is, this light source is emerging some light rays which are entering from this slit into this collimator. They are traveling, they are traveling, they are made parallel from by this convex lens. They are again traveling above this prism table, because there is no prism now. This prism table is blank, there is no prism, so they will directly travel to the convex lens of this telescope, right? Again, this telescope will converge them and this will focus them on the eyepiece, right? And on this eyepiece, I am seeing the image of this slit. On this eyepiece, I am seeing the image of this slit. This slit, or you can say the light source, can be changed like this. If I drag this slit focus, then it will, I can see, it is changing, right? It is focusing. It is going out of focus again. Initially, it was out of focus, and in last, it is going again out of focus. So in between, in middle, it is actually very good focused. This line you can see is actually very good focused. Again, the slit width can also be changed. You can see the width of the slit can be changed, and the intensity as well as the width of this light ray can be seen, right? As you can change the slit width, as you are changing the slit width, this line, this light ray, this line is increasing or decreasing in the intensity as well as in width, right? Now, on prism table, you can see there are two scales, two vernier scale, and they are supplementary to each other. They are supplementary to each other, and both of them will be 180-degree apart from each other. Now, why there are two vernier scale? You have to take observations from both the vernier scale. You have to do the calculations from both the vernier scale of the same observations, and it is just to reduce the errors, because suppose in any particular case you are not able to establish a very good vernier scale, a very good vernier scale matching, then in that case maybe in vernier 2 scale you are able to get a very good vernier scale reading. Okay, then in both the cases you will take some average for both the case, for both the observations of vernier 1 and vernier 2, you will take some average values, and hence the error will reduce, right? So this way, this prism. Okay, now before going into experiment, I just want to see the actual least count and the scales of this observation, this particular scale. So yes, you can change the angle of this telescope, either you can rotate. Okay, now the next thing is I can see you can rotate the telescope. You can see I am rotating this telescope, as I am changing this slider, the position of telescope is changing, right? The position of telescope is changing, and yes, as the angle between this collimator and this telescope is changing, hence the observations, the readings on this vernier scale is also changing. I have told you this vernier scale will give you the angle between this collimator and the telescope, right? So can you tell me what is the least count and what is the minimum main scale division, minimum main scale reading in this particular scale? So I will move slightly a telescope more so you can have. Okay, now you can see this vernier scale has points from 280 to 90. And okay, forget about the vernier scale, just tell me what is the minimum angle which can be measured by the main scale.
Half degree.
Half degree, are you sure? Okay, now you can see it is 281, 282, 283, 284, 285. Yes, and in each degree there is another a small line which corresponds to half degree. So the main scale observation, the main scale, the main scale has least count of, you can say, the main scale has observations of main scale divisions are 30 minutes. I will write. Okay. Now I will see the vernier scales. Now I will see the vernier scale. Again, there are 30 divisions in this vernier scale, and I have to check, you have to check that how many divisions on main scale these 30 vernier scale divisions are coinciding. But yes, I know it is 29, so I will just write. You can verify it from this figure also. 29 by 30 VST. Okay, so 29 by 30 MST. So for least count of this, I have to subtract this VSD minus from MST. So it will give me 1 by 30 of 30 minutes. Yes, the least count of this device, this particular device which they are using is 1 minute. The least count of this particular device is 1 minute. And can you also tell me at this point, okay, so another thing, this telescope can also be changed. This telescope can also be, the position of this telescope can also be changed by fine tuning of this telescope. You can see in this, by changing this slider, the position was changing very fast. But by for fine changing this telescope, you can also use this slider. It will slightly change the. Okay. So I will show you how to take observations and what was the cross section. Suppose, okay, I will close this. This was our source, and this was, I am rotating my telescope so that I can view the slit through this telescope. Okay, now in my image, in my view, the slit is coming. I have to rotate this telescope so that my slit exactly matches with this cross wire. These lines, these white lines and this perpendicular white lines are actually called cross wires of this telescope. I have to, for any observation, I have to match exactly the slit onto this cross wire. Now is the time you can take your observation. Now is the time, because now the slit is perfectly placed at the cross wire. You can take the observations on the scales now, right? So if I just give me one observation, can you give me one observation of from this scale? Can you tell me what is the observation of main scale division?
So 314.
314. 314. Okay.
Yes,
And main scale division? You are saying 314.
yes, sir.
Okay. Is anyone feels that it is 314 minutes? Sorry, 314 degrees 30 minutes?
No, sir.
Because we can see the zero of this vernier scale is just below this point. The zero of this vernier scale is just before this division. So it has to be 314 degrees. Okay, tell me the vernier scale. Vernier count.
Sir.
Yes, tell me. It is looking like we have a
10th
matching.
division.
10th division. We also have a matching at 20th division. I can also say I have matching on 30th division, right? But you have to see which division is actually coinciding with each other. Yes. किस पे जाएंगे बताओ? 10th, ओके 20 तो थोड़ा सा आउट ऑफ वो है, 20 तो आई कैन से थोड़ा सा स्लाइटली डिफरेंट है, 10 और 30 मेरे को सही लग रहा है। बताइए किस पे जाएंगे, 10 पे 10 मानेंगे या 30 मानेंगे? 30 मानेंगे, ओके। अगर 30 मानेंगे तो फिर ये मानना पड़ेगा आपको कि ये एग्जैक्टली कोइंसाइड कर रहा था, बिकॉज 30 into 1 minute will be 314 degree 30 minutes. Then you are saying if 30 is matching, then you are saying 0 is also matching. Are you getting my point?
Yes, sir.
Are you
Yes,
getting
sir.
my point? If you are saying 30th division is matching, then that you are actually saying that this 0 was coinciding with 314 degrees and 30 minutes on main scale. So
Sir.
I okay, ये आप खुद से देख लीजिए, इस पे कोई वो नहीं कर सकता है। Every eye has different perception. Every eye has different perception, but it should not vary considerably from person to person. So that observation was, let's say 314 degree, and some says let's say कि 28 पे fall कर रहा था, कोई कह रहा 29 पे कर रहा था, कोई कह रहा था 30 पे कर रहा है. So there is some window of error, not a problem. So the total observation will become 341 MSR main scale reading plus vernier scale reading will be 28 into 1 degree 1 minute, and the total reading will be 314 degree 28 minutes. You have to write all the observations in similar fashion. You have to write all the observations in similar fashion. You have to write main scale reading, you have to write vernier scale reading, and then you have to calculate the total reading. Right now, on the same position, I just want to find the observations on vernier 2. Can you tell me what are the observations on vernier 2? Again they will be 134 something, right?
Yes, sir.
Yes.
Again they will be 134 something. So this was from vernier scale 1, and from vernier 2 I am getting 134 degree and something. But you can see, as I was telling you, both of these scales are supplementary to each other. There will be 180 degree difference between these vernier scales, and you can, and if you calculate the observations, you can calculate, if you calculate the results from both of these scales, yes, error will be reduced. We will see in example. Okay, so now what we have to do is we have to find the first experiment. We have to find angle of prism. See, a right prism suppose there is a prism in which all the angles are around 60 degree. Okay, all the angles are around 60 degree, but you have to, with the help of these experiments, you can calculate actually this A precisely, which is optically precise, I can say optically precise. Okay, geometrically तो आप 60s को बोल सकते हो, but if you find this angle optically, then yes, the observations will be very precise. You will see the angle will come something like this, 59 degree 45 minutes or 54 minutes, something like this. Okay, so that observation you can say with the help of this optics, you can find these angles in very precise way. So for finding this angle of prism, what you can do is you can simply, okay, I will show you with a presentation. You have to place इसमें नहीं है. You have to place your prism in this way. You have to place your prism in this way so that light coming from this collimator will fall on this prism like this, on one end and on another end also. And after being reflection from this prism, this light ray, I will view this light rays with the help of telescope. And the geometry of this configuration, reveals that the difference between the angles at these two positions of telescope is twice of the angle of the prism. If I find the angle, the position of this telescope at point A, let I am calling this point as A. Okay. I am calling this position of telescope as A. I am calling this position of telescope as B. So if I subtract the observations of these positions, then what I will get is I will get 2A, twice of A, where A is the angle of prism. The geometry tells me, okay, the basic geometry from school level you can use to derive that these light rays, when reflected from these edges of prism, they will form an angle 2A. These two light rays will form an angle 2A, which is twice of this angle A. Right? So what you can do is you can place a prism on this table, on that experiment. You can place, okay, now I will place a prism, right? And I can move this prism table. Such that require that type of configuration. Now I am moving my prism table and I want to see this type of configuration when your prism, edge of this prism, the angle which I want to find is exactly in the front of this collimator. Okay, like this. If I show you again this screen, the figure, see in this figure also the angle, the edge of the prism is just in the in the front of collimator, right? That's why I was moving this prism table in this fashion. Okay, if I zoom it, you can see, yes. So tell me, okay, so yes, this light ray will travel through this collimator and it will fall, this light ray will fall onto both surface, because this is a parallel wavefront. This wavefront will be will incide on this surface also, on this surface also, and from this surface, let's say light is coming like this with my arrow. Try to visualize with my arrow, light is coming like this, and it is a broad source, you can say. It will fall onto this edge of prism and it will be reflected in this direction. Similarly, light ray is also coming and also will be inciding on this edge, and it will be going onto this direction. So I have to rotate my telescope in this direction, and I have to rotate my telescope in this direction. And I will note down the observations of both the cases, and then I will subtract those observations to get 2a, twice of a. Right? So, okay. Now I have to change my telescope position. I can change the telescope position by like this. Want to see where I can view the slit. I'm changing it slightly. Now you will see at some angle, yes. Now you can see at this angle, at this particular angle, I am observing the slit. Right? So if I zoom it again, you can see at this particular configuration, you can see the light is coming from this end, from the collimator. It is striking this prism at this point, and it is being reflected in this direction, and because of it I am seeing this slit, the slit on my eyepiece. Right? Light is coming in this collimator like this, it is being reflected from the prism, and it is going into the telescope, and because of which I can view the slit. Right? Now at this point, as my slit is actually coinciding with the crosswire, at this point I have to take the reading. I have to take the observations on both the scales. On both the scales, I have to take the observations. Roughly, I just want to see what is the observation of main scale. 129, sorry, 299, 298, 297. Okay. So on vernier scale 1, okay. On vernier scale 1, my observation is 290. My vernier scale 1, my observation was 297 something. Okay. Similarly, I also want to find the observation on vernier scale 2. And on vernier scale 2, it will be 119, 118, 170. Right? It is 170. Okay. I will call this as position 1. Again, I will change the position. I will change the position of telescope, and I will try to look the reflected ray from this side now. Okay, for this I have to move my telescope. And I want to see the reflected light coming in this direction. Okay. Okay. Now you can see at this point, I can see the slit coming from the collimator, and after being reflected from the prism, I am getting these observations. So again, note down these observations. These are actually on vernier scale 1. They are 60, 59, 58, 57. Right? So on vernier scale 1, the observation is 57. On position 2, in position 2, the vernier scale reading is 57 degree. Right? And vernier 2, in the same position, vernier 2 is showing me the observation 39, 38, 37. Okay, roughly it is 237 degree. 237 degree. 237 degree. Okay, I will just, okay, this corresponds to 2a. Okay, as seen from figure, this corresponds to 2a. I have just calculated this angle, the angle between the two positions of the telescope. This is 2a. So this 2a, if I calculate, if I decrease, it will be 237 minus 107 is 120 degree, right? But now another problem, a very common problem. If you decrease this 297 from 50, if you decrease this 57 from 297, it will come 240. Is it true? Is it right? See, vernier 2 was giving the difference as 120 degree. Vernier 1 is giving difference like 240 degree. See, in circular scales, suppose this is 0, this is 60, this is 120, 180, 240, 300, and 360 will also be here, right? So suppose you have two different observations, point A and this point B, and you want to find the difference of this. You can find it by directly subtracting the observation point of B from the observation values of A. Let's say this is 150, this is 70, let's say. So the difference between this position A and B will be of 80 degree, right? But if you cross this 360 division, if you cross this 360 thing, suppose your position, a position C is here and a position D is here, then the observation values of this, let's say, is 320 and of this is 50 degree. Then, and it has moved, the telescope has moved this much only. Then mathematically, if you subtract this 50 from 320, it will give you 270 degree. But that is not true. This telescope has not moved with 270 degree. So for that, what you have to do is you have to 360 minus the observation obtained in first position plus the observation from 0 to this 50 degree, right? Because the total path, the total angle covered by this during this motion is only this one plus this one, right? And this can be calculated, this part can be calculated by this 360 minus 320, and this part can be calculated from this 0 to 50. So the correct way to calculate this positional change is you have to write 360 minus 297 degrees plus 57 degree. So if you calculate this, this will be 63 degree plus 57 degree. So it will again come to 120 degree. So in both the cases, we have seen 2A is coming to be 120 degree. So A will be 60 degree. Roughly. I am not considering about the vernier scale. I am not bothering about the vernier scale. But if you calculate, if you observe vernier scale also, then there will be some values like 40 minutes something, okay, and let's say 28 minutes something. So there will be some more accurate value of 2A, and hence you can, yes, you can find uh, the angle of prism optically by this method, and it will give you a very precise value. It will not give you a rough value which is 60, it will give you a very precise value, right? So okay, again, if you are encountered this slit onto your crosswires onto your frame, Then also you can fine tune the telescope just like this. In this case, it is very decreasing very less. It is moving very slowly. Okay. To actually place it in on crosswire, you can use this fine angle of this. Again, also you can move this vernier table slowly with the help of this fine angle of vernier table. Okay. These angles will change drastically the values of prism table as well as this telescope, and these controls will change the value slightly, as you can see, right? These will change values very slightly, and these will change values very fast. So with the help of this, you have to calculate two different positions of telescope on these positions you are viewing the reflected ray from the prism. You have to take difference of these observations, and with the help of these observations you can find the angle of prism, right? You can find the angle of prism. But now the question is, we have considered that if this is our angle of prism, if this is our prism and light ray is coming like this, and after reflecting from this surface we are viewing this light ray on these positions, and the angle between this we are considering as 2a, and this angle between these positions is twice of this angle a. Now with the help of geometry, you have to, okay, if I extend these light rays, this will meet here. So basically this angle is 2a and this is twice of this angle. Okay. This you have to prove geometrically. This you can prove like 9th or 10th class में जो geometry पढ़ते थे, you have to prove that this angle will be twice of this angle. You have to prove that. This is your homework. Make some triangles like इसको अगर आप ज्वाइन करते हो, कैसे भी करिए, इसको अगर ज्वाइन करते हैं, यहाँ पे एक लाइन क्रिएट करते हैं, इसको करते हैं, तो लेट्स से दिस इज a, दिस इज x, दिस इज y, दिस इज z. तो ट्रायंगल एक्स वाई जेड में ये एंगल ये होगा, ये भी एक एंगल होगा, ये भी एक एंगल होगा, यहाँ पर भी एक एंगल होगा. So after all the considerations you can do anything, but in last you have to prove, let's say this is m, this is o, let's say this is m, this is o, this is n, right? You have to prove that angle MON is twice of angle of prism. You have to prove that. Right? Can you do this experiment? Now, I will share the link of this website. I will share the link of this website in your chat box. You may have to log in into this with the help of your Google account, and then you can perform this experiment. But yes, before performing this experiment, you have to find the least count of this given spectrometer, and you have to, in very clear way, okay, I will also show you how you have to make observation tables. See, okay, in this way you have to make observation table. Telescope reading for reflection from first phase, and second phase, the main scale divisions and the vernier scale readings, and then total reading in degrees. Similarly, from second phase in vernier 1, you have to do this. Then you have to find the difference of these vernier 1 from vernier 1 of position 1 and 2. This will give you 2A. Similarly, vernier 2 will also give you a 2A. Both separately, for both the cases, you have to find A by dividing it by 2. Similarly, there will be another A, and you have to take average of both of these A, mean A. Okay, this will be a single column. This will be a single row, mean A. Okay, so this also I will give you. Right. So you have now link. You have now observation table, a blank observation table. You have to make it. You have to make a very clean observation. You have to note down the observations and you have to do these calculations and you have to find the value of angle of prism.